Well, since we have a q-analog of binomial coefficients, of course we have a q-analog of multinomial coefficients as well. So first of all, let's recall what we used. That is too high. Let's recall what we used the multinomial coefficients for. So if we have a weak composition of n, and let's say capital M is the word that has A11s, A22s, etc., up to AMMs. Then the number of rearrangements of this word is n choose A1, A2 up to AM, which is n factorial over A1 factorial, etc. up to AM factorial. And our first proof is that there's n factorial ways to rearrange all of these n letters. And then we have to use the division principle to say, well, we're lying if we say it's n factorial because all of these ones look exactly the same. So we could permute them in A1 factorial ways and get the same word, and all the 2's look the same, so we could permute those in A2 factorial ways. So there's n factorial ways to permute n letters, and then we use the division principle to correct for overcounting of A1 ones, etc. So n factorial divided by each of these cardinalities factorial. Now I want to do a new proof of this. And this is going to lend itself to the Q analog. Let's define a bijection phi from the rearrangements of this word M and permutations of A1 letters and permutations of A2 letters, etc. to Sn by sending, let's say, W superscript 0 is the rearrangement of this word with repetitions, and let's say W superscript I is a word in the symmetric group AI. So let's send this m+1 tuple of a word rearrangement and m permutations to a permutation U in Sn, where we replace the AI occurrences of letter I in M by AI letters in the order described by WI. So we'll take the A1 ones and replace them with 1 through A1. In the order given by W superscript 1. And then we'll replace the A2 twos with A1 plus 1 through A1 plus A2 in the order given by W superscript 2, etc. So let's do an example of that. Let's say we have 2 1s and 3 2s and 3 3s. So we'll look at the map phi from rearrangements of that word, cross permutations in S2, cross permutations in S3, cross more permutations in S3, to S8, because we've got 8 letters here. So let's look at the rearrangement 2 1 3 3 1 2 2 3 and the permutations 2 1 2 3 1 3 1 2 2. So we'll make 8 spaces 1 2 3 4 5 6 7 8 to go along with these 8 letters. And I'll label the spaces just to make things easier for myself. Alright, so we have 2 1s. We're going to replace those with the letters 1, 2 in the order specified by the permutation S2, 2, 1. So we're going to put a 2 and a 1 where the 1s were, in that order. Then we'll take the 3 2s and replace those with the next 3 letters, 3, 4, 5, but in the order specified by 2, 3, 1. So that would be 3, 4, 5, like that. So 4, 5, 3. So where the 2s are, we'll put 4, 5, 3. Then we're going to replace the 3 3s with 6, 7, 8, but in the order specified by this permutation. That would be 8, 6, 7. So the 3s are in these positions, 8, 6, 7. So this is the bijection that takes this rearrangement, 3 permutations, to a big permutation. And you can see that we can undo this given the permutations here and the original word. So the important property of this bijection is that if U is the result of this algorithm applied to a word rearrangement, and M permutations, then the number of inversions in U equals the sum of the number of inversions in each of these, well, word or general permutations. And the proof is that each inversion in U, now U has distinct letters, is either a pair of letters that were both I in M, well, M being, say, W superscript 0, but different in W superscript I, and out of order there. Or there are pairs of letters that were different in W superscript 0. And out of order there. So like the 2 and the 1, or the 3 and 1, or the 3 and the 2. So that means every inversion in U either comes from, well, it comes from an inversion in exactly one of these permutations or this word rearrangement. Alright, so now we come to the Q's. So I claim that if we're looking at inversions in a rearrangement of some word M with repeated letters, so in particular, I guess I'll write this out, A1 ones, A2 twos, etc., AMMs. This equals the q-multinomial coefficient quantum n, choose quantum A1, quantum A2 up to quantum AM, which we'll define by quantum n factorial over quantum A1 factorial, quantum A2 factorial, etc., up to quantum AM factorial. So by the bijection phi and the claim about number of his inversions, we have that Q, if we sum Q to the number of inversions in W naught, well, W superscript 0, and that is in the rearrangement class of M. And multiply that by Q to the number of inversions in W1, where W superscript 1 belongs to SA1, and multiply all these sums of powers of Q, here Q to the number of inversions in WM, where WM belongs to SAM. By the bijection, that equals the sum of Q to the number of inversions of U, where U varies over all permutations in Sn. Now this equation is, here we don't know an expression for this. This is what we're really interested in. If we wanted a generating function for numbers of inversions in rearrangements of this word with repeated letters, what is it? But we know generating functions, we know nice expressions for all of these other factors and for the right hand side. So this equation is something unknown times, we know this is the Q analog of A1 factorial, and we know that each of these is the Q analog of that multiplicity factorial. And then the right hand side is just the Q analog of N factorial. So that means that our unknown thing, the first sum, which I guess I'll write out here, equals Q analog of N factorial divided by all these Q analogs of other multiplicities factorialed. So for example, if we let M be 1122233 again, then if we take Q to the number of inversions of, let me just say W, where W is in the rearrangement set of M. So the sum is another way of saying K equals, the sum from K goes from 0 to some max value of K. Not sure what it is. The number of permutations in the rearrangement class of M such that number of inversions of that rearrangement equals K, Q to the K. So next to Q to the K we've got the number of rearrangements having K inversions. This is 8, quantum 8 factorial over quantum 2 factorial, quantum 3 factorial, quantum 3 factorial. The end.